Hello, welcome. In the previous lecture, we talked about vectors in Rn, and we introduced the notion of vector spaces. We defined the concept of vector in abstract or general spaces. In this part of the lecture, we're going to talk about subspaces of vector spaces. What are subspaces? Suppose we have a vector space V and consider a non-empty subset W of the vector space V. If we can show that this subset W is a vector space, then we would call W is a subspace of the vector space V. In short, subspace simply stands for a non-empty subset plus it is itself a vector space. Let's have a look at the formal definition of a subspace of a vector space. Definition: a non-empty subset W of a vector space V is called a subspace of V if W is a vector space under the operations of vector addition and scalar multiplication defined in the vector space V. We note that the set containing the zero vector only is a subset of the vector space V, and the set V is also a subset of the vector space V. It can be shown that the set containing the zero vector only is a vector space. It satisfies all the 10 axioms in the definition of a vector space. These subspaces are called trivial subspaces of V. In this lecture, we will be interested in subspaces which are not trivial. Those subspaces are called non-trivial subspaces. In general, if a non-empty subset W of V is given, then we need to verify all the 10 listed axioms for the elements of W to be a subspace. However, the following theorem reduces this task to only 2 steps. Theorem: test for a subspace. If W is a non-empty subset of a vector space V, then W is a subspace of V if and only if the following closure conditions hold. The first condition: if U is an element of W and V is an element of W, then the sum U plus V is also in the set W. So property 1 says that W is closed under vector addition. Property 2 if U is an element of W and C is any scalar, then the scalar multiple of U, Cu, is also an element of W. So this property is known as that the W is closed under scalar multiplication. So if these two conditions hold, then we say W is a subspace for a vector space V. So this theorem is true in both ways. If W is a subspace of a vector space V, then the conditions 1 and 2 hold. Conversely, if the conditions 1 and 2 hold, then W would be a subspace of a vector space V. The proof of this theorem is straightforward. We can find it in the appendix of this note. Let's see a couple of examples of subspaces of a given vector space. Example. We want to show that the set of vectors with 3 components, where the first component x, and the second component is 0, and the third component is z, where x and z are real numbers, is a subspace of the vector space R3 with the standard operations of vector addition and scalar multiplication. For example, the vector -1, 0, and 3 is an element of the set W. Similarly, the vector 0, 0, 0 is also an element of W, because in each of these two vectors we see the second component is 0. So they met the condition to be in the set W. However, the vector with components -1, 2, 3 is not in the set W, since the second component of this vector is not 0. So surely W doesn't contain all the vectors in the set R3 space. It's a proper subset of the set R3. We want to show that W is a subspace of the vector space R3. Let's have a look at the solution of this problem. To show that W is a subspace of the vector space R3, we need to show that W is closed under vector addition and W is closed under scalar multiplication. So we take two vectors U and V with the components as shown from the set W. Then we add these two vectors, which gives this vector with the first component x1 plus x2, the second component is 0, and the third component is z1 plus z2. Since the second component is 0, the vector u plus v is certainly in the set W. So we proved that W is closed under vector addition. Similarly, if C is any real number, then the scalar multiple of U is the vector with components Cx1, 0, Cz1. Since the second component of this vector is 0, the vector is in the set W. So we proved that W is closed under scalar multiplication. Now, by the subspace test theorem, we can claim that W is a subspace of the vector space R3. Before we look into the next example, let's recall that an n by n matrix A is called symmetric if the transpose of A is equal to the matrix A itself. For example, if A is this matrix, then we can simply show the transpose of A is equal to A. Hence, A is a 3 by 3 symmetric matrix. Recall that a transpose of A is simply obtained by transposing the rows of the matrix A into its column. For example, since the first row of A contains the elements 1, 2, and 3, so when we transpose the matrix A, we got 1, 2, and 3 in its first column. Similarly, in this way, we got the transpose of A. Now we observe that the transpose of A is exactly equal to the matrix A. Hence, A is a 3 by 3 symmetric matrix. We can also simply observe that the first row and the first column is exactly the same. Similarly, the second row and the second column are exactly the same. And the third row and the third column are also exactly the same. So if this condition is met, we say a matrix is symmetric matrix. But the matrix B is not a symmetric matrix, since its transpose is not equal to the matrix B. For example, the first row of B is not same as its first column. Let's have a look at the next example. Let S sub 2 be the set of all 2 by 2 real symmetric matrices. We want to show that the set is a subspace of the set M2, 2. Recall that M2, 2 is a set of all 2 by 2 matrices. Let's have a look at the solution. We can let S sub 2 is a set of all matrices A in the set M2, 2 such that A transpose is equal to A. In other words, A is a symmetric matrix. We must show that S2 is closed under addition and scalar multiplication. To show that, we take two matrices A and B from the set S sub 2. Since the transpose of the sum of two matrices is equal to the sum of their transposes, then we can replace the transpose of A by A matrix, since A is symmetric. Similarly, since B is symmetric, we can replace the B transpose by the matrix B. So we found that the transpose of a matrix is the matrix itself. This shows that the sum of two symmetric matrices is also a symmetric matrix. Hence, A plus B is in the set S sub 2. Similarly, if A is a symmetric matrix and C is any real number, then by following the property of a transpose, the transpose of CA is exactly equal to the matrix obtained by multiplying A transpose by the scalar C. Now, since A is symmetric, we can replace the transpose of A by A. So we found that the transpose of a matrix CA is simply the matrix itself. Hence, CA is also a symmetric matrix whenever A is symmetric. Hence, CA belongs to the set S sub 2. Therefore, by the theorem 10.1.1, namely the test for subspace, we claim that S sub 2 is a subspace of M sub 2, 2. In fact, we can show the set of all n by n symmetric matrices is a subspace of M sub n, n. The proof is exactly the same what we did. Let's see a non-example. The set of all 2 by 2 singular matrices is not a subspace of the vector space M sub 2, 2. Recall that a square matrix A is called singular if its determinant is equal to 0. In other words, if A is a non-invertible matrix. So S is a set of all matrices in the set M sub 2, 2 such that its determinant is equal to 0. We want to show that this set S is a subset of the vector space M sub 2, 2, but not a subspace. To show that, we take two matrices A and B from the set S. Note the determinant of the matrix A is equal to 0. Similarly, the determinant of the matrix B is also equal to 0. So A and B are taken from the set S. But if we add these two matrices, the matrix we get has the components 1, 0, 0, 1, which is not in the set S, since its determinant is equal to 1, not 0. So we proved that the set of all 2 by 2 singular matrices is not a subspace of the vector space M sub 2, 2. Let's see another example. Let D denote the set of all differentiable real-valued functions defined on the bounded and closed interval a to b, with a strictly smaller than b. We want to prove that the set D is a subspace of the vector space C. Recall that C is a set of all continuous functions defined on the bounded and closed interval a to b. Let's see the proof. In example 9.2.4, we proved that the set C, which is a set of all continuous functions defined on the bounded and closed interval a to b, is a vector space. From calculus, we know that every differentiable function is continuous. Certainly, the set D is a proper subset of the set C, since not every continuous function is differentiable. We want to prove that the set D is a subspace of the vector space C. First of all, the set D is non-empty because the zero function, which is continuous function on the bounded and closed interval a to b, defined by the formula as shown here, is differentiable on the bounded and closed interval a to b. Therefore, the zero function belongs to the set of all differentiable functions. Now, to show that the set D is closed under addition, we take two differentiable functions, f and g, from the set D. Then from calculus, we know that the sum of two functions, f plus g, is also differentiable over the domain, the bounded and closed interval a to b. So, f plus g belongs to the set D. This proves that the set D is closed under addition. Similarly, if f is a differentiable function over the interval a to b, then for any scalar c, the function c times f, the constant multiple of the function f, is also differentiable over the domain, the bounded and closed interval a to b. Therefore, cf also belongs to the set D. This proves that the set D is closed under scalar multiplication. Therefore, by the theorem 10.1.1, the test for subspace, the set D is a subspace of the vector space of all continuous functions. This concludes the proof. Let's have a quick look of the subspaces of functions. It can be shown that the set of all functions forms a vector space. Then the set of all integrable functions forms a subspace of the vector space of all functions. Then the set of all continuous functions is a subspace of the vector space of all integrable functions. Since not every continuous function is differentiable, so the set of all differentiable functions is a subset of the set of all continuous functions. And we just proved that the set of all differentiable functions form a vector space, which is a subspace of the set of all continuous functions. And the set of all polynomial functions is a subspace of the vector space of the set of all differentiable functions. Linear combination. A vector v in a vector space V is called a linear combination of the vectors v sub 1, v sub 2, all the way up to v sub n in the vector space V if the vector v can be written in the following form. So V is equal to C sub 1 times V sub 1 plus C sub 2 times V sub 2 plus all the way up to C sub n times V sub n, where these C's are some scalars. Let's try to explain this with the help of an example. If V is a vector with components 1, 1, 1, then V is a linear combination of the vectors in the set S, where S contains these three vectors. Let's call them V1, V2, and V3. So we want to show that this vector V is a linear combination of these three vectors. Let's see the solution. To see if V is a linear combination of vectors in the set S, we consider the following equation. We want to find the scalars C sub 1, C sub 2, C sub 3 such that the equation is true. Or if we replace the vectors V sub 1, V sub 2, V sub 3 and V, we get this equation. Now the left hand side can be written as in this form, which is simply obtained by multiplying the first vector by C1 and the second vector by C2 and the third vector by C3, and just by then adding. So we have a column vector in the left hand side of this equation and a column vector in the right hand side of the equation. So these two vectors will be equal if and only if we have these equations hold true. So we have a 3 by 3 system of linear equations. We want to solve this system for the C1, C sub 2 and C sub 3. Now we form an augmented matrix of this linear system, which simply becomes this matrix. Observe here, the first column of this augmented system is none other than the first vector V1. Similarly, the second column and the third column are the vectors V sub 2 and V sub 3. And finally, the fourth column contains the components of the vector V that we want to show as a linear combination of the vectors V sub 1, V sub 2 and V sub 3. Now the row reduction gives this augmented system, which is in its reduced row echelon form. Now we identify the pivots which correspond to the variables C sub 1 and C sub 2. We see that the third row contains no pivot. So the variable C sub 3 is free. It means we can assign the value of C sub 3 as any real number. For example, if we assign C sub 3 is equal to 1, so the system gives the solution. Namely, the first row gives us the equation C sub 1 minus C sub 3, which is equal to 1. And the second row gives C sub 2 plus 2 C sub 3 equals to negative 1. And if we plug in the value of C sub 3 as we assumed to be equal to 1, we get this solution. So C sub 1 is equal to 2, C sub 2 is equal to negative 3, and C sub 3 is equal to 1. So we showed that the vector V is in fact a linear combination of the vectors V sub 1, V sub 2, and V sub 3. And the corresponding coefficients are C1 is 2, and C2 is negative 3, and C1 is positive 1. Please pause the video and try to see the solution again. Remark: the linear combination we obtained earlier is not unique. For example, had we chosen C sub 3 to be equal to 0, we would get C sub 1 is equal to 1 and C sub 2 is equal to negative 1. And this gives the vector V can also be written as a linear combination of the vectors V sub 1 and V sub 2, as shown here. So a vector V can be obtained in many different ways from the linear combination of the vectors in a given set. Let's have a look at another example. We want to show that the vector, in fact the matrix, which is taken from the vector space M sub 2, 2, is a linear combination of the vectors in the set S. In short, we want to show that the matrix V is a linear combination of the matrices in the set S. Let's have a look at the solution. We want to solve the following vector equation for the unknowns C sub 1, C sub 2, and C sub 3, such that this equation is true. Now, if we replace the vector V sub 1 by the matrix here, and V sub 2 by the matrix here, and similarly V sub 3 and V by the matrices as shown, then we get a matrix equation. The left-hand side of this matrix equation can be put into a single matrix, and the right-hand side stays as it is. And we know that two matrices are equal if and only if the corresponding elements are equal. For example, negative C sub 2 minus 2 sub C sub 3 equals to 0, and 2 C sub 1 plus 3 C sub 2 is equal to 8, and C sub 1 plus C sub 2 plus C sub 3 is equal to 2. And finally, we have 2 C sub 2 plus 3 C sub 3 equals to 1. So this is a 4 by 3 system. It has 4 equations and 3 unknowns. We would apply the formal method of solving a system of linear equations, which is called a Gauss-Jordan elimination process. If we form an augmented matrix from the given system of linear equations. Then, by a formal row reduction, gives the following matrices. Please pause the video and try to see the row operations. And finally, we get the reduced row echelon form of the given system of linear equations. Now we identify the pivots. So we have the solution. This means that the matrix we were given in the question can be written as a linear combination of the matrices in the set S, as shown here. Please try to verify the linear combination. Now let's try a non-example. The vector v with components 1, -2, 2 is not a linear combination of the vectors in the set S. To see this, we consider the following equation. We want to solve this vector equation for C sub 1, C sub 2, and C sub 3. Following the same procedure, we end up with this reduced row echelon form of the augmented matrix. The last row of this reduced row echelon form shows that the equation 1 has no solution, since the last row stands for this equation. Which is not true for any value of C sub 1, C sub 2, and C sub 3. Therefore, there exist no scalars C sub 1, C sub 2, and C sub 3 such that the equation holds true. Hence, the vector v is not a linear combination of the vectors v sub 1, v sub 2, and v sub 3. With this, we end the part 1 of this lecture. In the next part of the lecture, we continue to the spanning sets and linear independence and dependence. Thank you.